In this lecture, we will learn how to analyze plane frames by strain energy method. So, analyze the frame shown in figure using strain energy method and draw the bending moment diagram. So, in this frame, one support is fixed, another support is hinged, and the columns are of I moment of inertia. Then the beam has 2 times the moment of inertia of that of the column. So 4 meter height of the column is 4 meter height and the beam span is 6 meter. And we have one horizontal load at B support or B joint, and at the mid span of the beam we have 20 kilonewton. First we have to find out the reactions, number of reactions we have. Out of these reactions, what are the reactions are redundant, can be considered redundant. That is, we have to determine the static indeterminacy of the frame. Okay. So in this problem, for fixed support we have 3 reactions. Okay. That is RA, MA, HA, and for this hinge support we have 2 reactions. One is RD and one is HD. Therefore, ds is equal to total number of reactions, that is 5, minus total available equilibrium equations 3. So is equal to 2. Therefore, any 2 of the reactions can be considered as redundant. But to simplify the computations and analysis, we will choose the easiest or which reactions will make the entire structure as a stable, somewhat cantilever portions. Therefore, in this case, we will consider the reactions at support B as the redundant. Okay, so the structure will be a simple cantilever portion. So, from the Cauchy-Klingler's theorem of least work, the partial derivative of the total strain energy with respect to this redundant is equal to 0, because the support is not sinking or yielding, so is equal to 0. Otherwise, we have to assign that value, sinking value. So dou u by dou RD is equal to 0 and dou u by dou HD is equal to 0. So totally 5 reactions we have. We have only 3 equilibrium equations. So other equations, 2 equations required to solve the problem is dou u by dou RD is equal to 0 and dou u by dou HD is equal to 0. So from sigma H is equal to 0, so in the frame we have RA, RD and HA, HD. Here we assume HA and HD are acting towards the left directions. Okay, since the external force is acting towards the right side, right direction, we assume. Okay, in any direction we can assume initially. Suppose the answer is positive, our assumption is correct. If the answer is negative, then we have to change the direction. That's all. Okay, so here initially we assume HA and HD are both acting towards the left side direction. Okay, and MA acting in anti-clockwise direction. Now we can apply the sigma H is equal to 0, HA plus HD is equal to 10. because HA and HD both acting in the same direction, 10 is in opposite direction. So we are equating this. From this we can get HA is equal to 10 minus HD, because everything we have to convert into probably these two parameters, RD and HD. Then from sigma MA is equal to 0, this RD into 6 meter, okay, then minus 20 into this 3 meter, then minus 10 into this 4 meter, then MA is equal to 0. Therefore, MA is equal to 100 minus 6 times RD. For better clarification, we use the table form. So span, then limit, mx, and we have two redundancies. Therefore, we have to differentiate this mx with respect to RD and HD. So considering span AB, okay, here we have RA, HA, MA, and taking a section XX, which is at X distance from A. Therefore, the limit of this span is 0 to 4 meter. That means X can take a value of 0 and a value of 4 meter from A to B. A is at 0 meter, B is at 4 meter. Now taking moment about this XX section, HA into X. Okay, so positive moment. Then MA negative. Okay. So, but HA we know 10 minus HD, and MA is 100 minus 6 R. Okay. This is the expression for moment. Now we have to differentiate this expression, moment this expression with respect to first RD. Therefore RD here we have this minus plus, so plus 6. Similarly with respect to HD, here we have minus HD X, so minus X. Next span PE. Here we consider section X distance from C. Why? Because we need only this RD and HD to be involved in the expression. So even though we have converted this HA and MA in terms of RD and HD, if you consider the X from C, you can directly get RD and HD being involved in our expression. That's why we consider X from here. You can also consider X from B also, no problem. Okay. So here X distance, but our span is B. Therefore at E, the X value will be 3 meter. At B, the X value will be 6 meter. Therefore 3 to 6 meter. So taking moments about this X section, we have RD, is RD into X distance, RDX minus this HD into 4 meter. Okay, there other section is no problem. The distance of HD is constant. That's why 4 meter, 4 into HD. Then minus this 20 kilonewton into this distance. That means X minus this 3 meter. Okay. So with respect to RD, this X value, then differentiation with respect to HD, we have only minus 4. Next CE section. Okay. So X from C is joint. Therefore, 0 to 3 meter, up to E 3 meter. So there is RD into this X minus 4 into HD. Again differentiation with respect to RD is X, with respect to HD is minus 4. So in DC span, this is a section. So this X varies from 0 to 4 meter. Then here we have only HD involved. So HD into X, but negative moment, so minus. Then with respect the derivative with respect to RD is 0 here because there is no term RD in this moment expression. Then with the derivative with respect to HD is minus X. Now we can apply the Castigliano's theorem. That is dou U by dou RD is equal to 0 and dou U by dou HD is equal to 0 one by one. So dou U by dou RD is equal to 0. Here we have to keep in mind that the beam section is of 2i. Then we have to know very very careful while that is substituting the values in this expression dou U by dou RD is equal to 0. So for the column AB section, see we have only I, that means 1 by EI common. So 0 to 4, so this is mx value in the table and this is the dou U by dou RD into dx plus this is 1 by 2i because I is 2 times for PE section. Then this is the mx for BE section and the limit is 3 to 6 into x into dx. Similarly, EC or CE section 1 by 2 EI but 0 to 3 meter. This is the mx. This is the dou U, that is dou mx by dou R. Here this is the CD column 1 by EI 0 to 4. Then this is the mx and there is no term RD in the mx term, that is dou U by dou RD is equal to 0. So that this entire term will get cancelled, will be 0 for this condition is equal to 0. So therefore this is the expression after integration. So finally we get 180 RD minus 84 HD is equal to 2145. This is our first expression involving both parameters RD and HD. Now we will consider the next dou U by dou HD is equal to 0. So this is the expression. Okay, dou U by dou HD is 0 and after integration we are getting this x values. So finally we get 252 RD minus 272 HD is equal to 2300. This is our second expression. From first and second expressions we can solve the values for RD and HD. .55 kilonewton. RD is equal to 14.04 kilonewton. These two values, we can substitute these two values in our HA and MA expression because HA is equal to 10 minus HD. Therefore, HA is equal to 5.45 kilonewton. Then MA is equal to 100 minus 6 times RD. Therefore, MA is equal to 15.76 kilonewton. So now we have mostly all the required parameters to find out the internal forces, that is joint moments, so that we can draw the bending moment diagram. So considering the free body diagram of AB, so this is our AB and here we have horizontal reaction HA, this is our vertical reaction RA, this is our moment MA moment 15.76, this is 4 meter length, and at B we have one external force 10 kilonewton and we assume this MA is acting anti-clockwise motion. Okay. in any direction. Now we can assume initially. If we get positive value, then our assumption is correct. If negative means the direction is just opposite. So consider the free body diagram of AB, then taking moment support B. Okay. So we have MP is equal to this HA into 4 meter minus MA. That's all. Because this is acting through the B, therefore there is no moment contribution from this RA. Therefore MP is equal to 6.04 kilonewton meter. Okay. So in AB, this MP is acting in anti-clockwise direction, but for BC column, this MP will act in opposite direction. Okay, that is in the clockwise direction. Now consider the free body diagram of CD. Here we have RD reaction, this is the HD, 4 meter. Then initially we assume the anti-clockwise direction for M's. So taking moment support to C, MC is equal to HD into 4. So 4.55 into 4, MC is equal to 18.20 kilonewton. So positive answer, therefore our assumption is correct. That is MC is acting in anti-clockwise direction in column C. To draw the bending moment diagram, we need the simple support moment for the span BC, so that we can overlap with the support moment diagram. Therefore, this is simply supported case for BC with loading. Therefore, the maximum moment happens at E, because there is no loading here in B and the EC section. Therefore, M is equal to WL by 4 is equal to 30 kilonewton meter. So we have all the data. Therefore, we can start the bending moment diagram, drawing the bending moment diagram. So this is the moment in AB column. So here we have MA moment. Here this is the MB moment. Similarly for CD, this is 0 moment here. This is the moment MC moment. So for BC column, this is again just opposite moment here. Here also MP in opposite direction here. Therefore you have to join these two. Okay. So I use a different color too, so that we can easily identify the moment diagram for different number. So this is negative here also negative moment. Now over which we have to superimpose the single supported moment. At center we have 30 kilonewton meter. Okay, so this is our 30 kilonewton meter. Okay. So 15.6, 15.76, 6.04, this is also 6.04, 18.02, this is also 18.02, this is 30 kilonewton meter. But this portion is get cancelled. Okay, we have only this portion. I will show you in yellow color or the dark. Yes, pink color, using pink color. So this is the bending moment. This also included. So this portion get cancelled. Okay. So this hatched area is the actual bending moment diagram. Okay, this is the end of this session.